Hi guys, this is Ashish Manglani and today I'll be discussing the solutions to the Codeforces round 815. So let's begin with problem A. So in this problem you are given two fractions a by b and c by d, and in one operation you can multiply either the numerator or the denominator of one of the two fractions by any integer of your choice. Okay, and you want to make the two fractions equal, and you have to find the minimum number of steps to make these fractions equal. So let us see what the problem statement is. So we have been given with a by b and c by d. So the base case is like it will take zero operations if a by b is equal to c by d, and let's see like can it take one operation or not. So at max, if you think it will take two operations. Like you can find the LCM of both the fractions, and then you can multiply a by b with LCM divided by a by b and c by d with LCM divided by c by d. So at max it's gonna take us two operations, and let us see like when can we do it in zero operations, one operation or two operations. So for zero operations your a by b has to be exactly equal to c by d, and let's see the case when we have to do one operation. So the since you can multiply it by any integer, so one of the cases like when either a is equal to 0 or c equal to 0, then you can just multiply the other integer by 0 and both fractions will become equal to 0. So that's going to take us one operation. So if either a equal to 0, so if either a equal to 0 or c equal to 0, then it's going to take us one operation. And if both of them are 0, then the fraction is already equal to 0. Like the values of b and d doesn't matter. So if a is equal to 0 and c is equal to 0, then it's not going to take us any operation because the fractions are already equal. Otherwise, if one of them is 0, we can multiply the other fraction by 0, like the numerator of the other fraction by 0, and both of the fractions will become equal. And so that's the case of one operation. And let us see when can we achieve the answer by one operation. So let us say that we need to multiply a by b by some x, like we multiply the numerator by some integer x, and that becomes equal to c by d. Okay, and this becomes equal to c by d. So the thing is like if you notice that multiplying a by b, like the denominator of a by b with x, like what I mean to say is that multiplying the denominator of a by b with x is same as multiplying the numerator of c by d with x. Like if you want to make this equal to this, you can like cross multiply this x over here, and so multiplying the denominator of a by b with x is equivalent to multiplying the numerator of c by d with x. So we'll check two of the cases. So one of the cases will multiply the numerator of a by b with x, and will multiply the numerator of c by d with x, and we'll try to equate both of their fractions. So let's try the first case when we multiply the numerator of one of the fractions by x. So x is an integer that we choose, and this becomes equal to c by d. Let us try to rearrange the equation. So in that case, x is equal to b into c, b into c divided by d into a, d into a. So if the answer exists, like if we can equate both of the fractions by just multiplying with an integer x, then this x has to be an integer. That is, b multiplied by c should be a multiple of d into a. So d into a should divide b into c. So this is the condition for achieving the answer with just one operation. In the other case, when we multiply c by d with x, like a by b is equal to c by d into x. So in that case, your x comes out to be a into d, divided by b into c. So in this case, for x has to be an integer, then a into d should actually be divisible by b into c. So it's gonna take you one operation if either this is an integer or this is an integer. Otherwise you can always achieve the answer with two operations, because like if this thing is actually not an integer, then this thing is represented by some form p by q, and you can always replace x with p by q such that you multiply a with p and b with q. So in that case you can always achieve the answer by two operations. So this is what the solution is. I'll go over my code once. So let me zoom it. Okay, so I take my input a, b, c and d. So if either a is equal to 0 or c is equal to 0, then my answer is 0, because like if a is equal to 0 and c equal to 0, then my answer is 0, because the both of the fractions are already 0 and I do not care about the value of b and d. So this is like a trivial case in which many people might have failed the system testing, because in this case only the value of b and d doesn't matter, and if one of the fractions is 0, then I can always multiply the other fraction by 0, and I can achieve an answer of 1 by just multiplying the other fraction by 0. Otherwise I try to represent, first of all, like I try to represent this a by b and it's like the least possible form. So for example, if you talk about this case, 6 by 2 and 3 by 1, so the fractions are actually equal, because since 2 divides this and 2 divides this, so this can be represented as 3 by 1. So first of all I try to represent my fractions in the minimal possible way. So I take the GCD of a and b and I divide a by GCD and b by GCD. Similarly I take the GCD of c and d and I divide c by GCD and d by GCD. Then I check if my a is equal to c and b is equal to d. In that case my fractions are already equal and I need not perform any operation. So the answer is 0. Otherwise, this is the condition that I told you. If either this thing is divisible, if either b into c is divisible by d into a, or a into d is divisible by b into c, then I can perform only one operation and get both of the fractions equal. Otherwise, I need to spend two operations. So this is the solution for problem A, and let's move on to problem B. So in problem B, you're given an array of n integers, and you can choose any subsegment, any proper subsegment from L to R, and you have to maximize the value of this operation, of this expression. So what the expression is, like if you select any subsegment from L to R, so in that case you take the maximum of the remaining elements, like the elements excluding the range L to R, and take the minimum of the corresponding range, take the difference, and then add to it the maximum of the range of L to R minus the minimum of the range L to R. So let us see like what this expression actually is. So suppose we select a range L to R. So let's say this is my given array 1 to n, and I select this range L to R. This is L, this is R. Then I take the maximum and the minimum of this range L and R, and I add max minus min to my answer, and I add max minus min to the answer, and from the remaining range I take the maximum value of the remaining elements. I take the max of the remaining elements and I subtract it by the minimum of the remaining elements, and we have to maximize the total sum, like the maximum of the range that we are taking minus the minimum of the range we are taking, plus the maximum of the excluded range minus minimum of the excluded range. So, and we have to find the maximum value of this expression. So let us try to maximize the maximum number that we have, like let us try to maximize the positive terms and minimize the negative terms. So to maximize the maximize the positive terms, what we can see is that the maximum possible value that we can achieve is the maximum of the array itself. So for the maximum, like for the maximum part, the maximum value that we can achieve is the maximum value of the array itself. So let us say my array looks like this, and this is the maximum value of the array. Let's say this is the maximum value of the array, And now I want to minimize this negative part. To minimize the negative part, what I will try to do is like take the minimum value of the array. Take the minimum value of the array. So initially, first of all, like what can our maximum answer be? Like we have to take uh, two of the maximums of a non-intersecting range and two of the minimums of the a non-intersecting range, because not by non-intersecting I mean that either you take the elements from the corresponding range or you are taking the elements from the excluded range. So these both of the segments are non-intersecting. So you can, the maximum possible answer that you can achieve is the two maximums of the array. Like these two maximums of the array will contribute to the maximum part. So max 1 and max 2 of the array, like the two maximum possible values of the array minus the two minimum values of the array, two minimum values of the array. And you cannot actually improve your answer because this is the maximum answer you can get. Like you can take the positive elements to be the maximum values in the present in the array, and you can take the negative elements to be the minimum possible values of the array. And let us see, can we always achieve this answer? So let us say that the minimum of the array lied somewhere over here. So like I said, this is the maximum value of the array, and let us say the minimum value of the array lied somewhere over here. Then in that case, uh, one possible way is that I select this segment. I select this segment as my L2R. So now the case is the second minimum of the second minimum of the array lies in this range, like the excluded range, and the second maximum of my array also lies in the excluded range. So in that case, I will be able to get my answer. So let me say this is the second max, this is the second max, and this is my second min. So in this case, I'm able to achieve my answer like max minus min, like total max minus total min, and the second max minus like second max minus second min. So I'm able to achieve this answer. Let's see what can possibly go wrong. So let me say that this is my maximum element, like the total max of the array, and this is my minimum element, like the total min of the array, and my second max lies somewhere over here. In this case, my second max lies somewhere over here. So if I try to take this range from max to min, then I will basically lose out on the second element itself, like second max itself, because uh, I cannot take this range again. I cannot consider this range again. So if I consider this range after taking this as L2R, then in that case the maximum of this range would actually be lesser than the second max, because second max is also included in this range. So what I can do in that case, instead of taking this segment as L2R, what I try to do is I try to find my second min of the range. So let us say that the second minimum appears somewhere over here. So this is the second min, like the second most minimum element of the array. So in that case, I take this range from L to R. So this range contains the maximum value of the array and the second minimum possible value of the array. So this contributes to the positive part and this contributes to the negative part. And in the other case, like in the excluded part, this will be the maximum value because this is the second max, and this will be the minimum value because this is the minimum of the whole array. So in this case also, this will contribute to the positive part and this would contribute to the negative part. So again, I have the two maximums of the array as the positive part and two minimums of the array contribute as my negative part. And what can the other case be? So let us say that my minimum element lied somewhere over here. So my minimum element, like the second minimum element, lied somewhere over here. So in that case, instead of taking this L to R or this L to R, what I can do is like I can take this range as my L to R. So this range contains the second max of the array and the total minimum of the whole array, like the least element of the whole array. and the excluded range in this case would contain the total max of the array and the corresponding second minimum element of the array. So if you try out the case work, this always exists a way in which you can have a second, like in which you can have two non-intersecting subarray, like two non-intersecting subsegments. So let's say this is my L2R, and there can always exist a case in which either the maximum of the array or the second maximum of the array lies in this range, and either the minimum of the array or the second minimum of the array lies in this range. And correspondingly, what I would have is the first minimum or the second minimum would lie in the remaining part, and the first maximum and the second maximum would lie in the remaining part, like the other remaining part. So it will always be possible to have the two maximum values contribute to my positive part and two minimum values corresponding to my negative part. So that's the solution for the problem. So how do I implement this? Is that uh, so I take my input array and I sort all the values, and I take the two maximum values of the array as my positive part and the two minimum values of the array as my negative part. And this is my answer for the second problem. So you can try out the casework and you can see why it is always possible to take two maximum values and two minimum values as the corresponding answers. So let's move on to problem C. So in problem C, you are given a matrix consisting of n rows and m columns, and this is a binary matrix, that is each of the value is either 0 or 1, and you select a L-shape element. So L-shape element is basically a 2 cross 2 square with one of the cell removed. So you can select any L-shaped element that contains at least one cell containing 1 and replace all the numbers in it with zeros, and you have to find the maximum number of operations that you can do with the given matrix. So let us see what the problem is. So let us see some of the test cases that are present in the input. So let me try out this test case. So 101 and then 111 011 111 011 and 110 110. So what the problem says is you select any L-shaped element. So L-shaped element looks like this, and it can also be rotated. Like it can also be like this, and it can also exist like this. So these are all the possible L-shaped elements, and in one of the operation you select a L-shaped element that contains at least one, and you replace all the elements by zero. So in one operation, if you select this L-shaped element, you replace this cell, like you replace this value by 0 and you replace this value by 0. And let's say in the next operation, you select this element as your L-shaped L shape, and since it contains at least one and these two elements are already 0, so you replace it by 0. And like similarly you perform other operations, and finally you have to convert the whole of the matrix to zeros, and you have to find out the maximum number of moves that it takes to convert all the values to 0. So this is basically a casework type of solution. So how did I arrive at the solution? Like how did I arrive at the casework solution is that by considering what happens when I have a full binary matrix. And by what I mean by full binary matrix is that, let's say all the values were 1 initially. So now no matter what L-shaped element that you choose, you would always lose out on 3 ones in the initial step. So let us say I chose this element, and in one operation this will become 0, this will become 0, and this will become 0. And in the next operation, what I can do is that I can extend this thing to like this. Like I have two corresponding zeros at these two positions. What I can do is I can always extend these two zeros by 1. So in my next operation would be like something like this, and in my next operation this thing will also become 0. And similarly in the next operation I select this shape as my L-shaped element and I convert this to 0, and in the other operation I select this shape as my L-shaped element and I convert it to 0. So basically, if you notice is that in the first operation only, I was losing out on 3 elements, and after I converted these 3 elements to 0 in one operation, I can always convert only 1 0 to a, like, only 1 1 to a 1 in one operation. Like, what I mean is that if I perform an operation after perform, like, from the second operation onwards, if I perform any operation, I'm not gonna lose out on more than one ones present in the array. So let me say that this these both values became, like, all three values became 0 after one operation. So there would always exist one operation such that you would only lose out only one of the ones. So for example, there is this operation, this L-shaped element, and if you perform the operation on this L-shaped element, you're only gonna lose out on this one, and your rest of the ones are safe. So so if you have a full binary matrix, then the number of moves that you can perform is the total number of ones present in the matrix minus 2, because in the initial operation, in one move you are losing out on 3 elements, and from further operations, in one operation you are losing out only on 1 element. So if you have a full binary matrix, you can perform n minus 2 moves. So, like, we see that the maximum, like, these are the maximum number of operations that we can perform, and let us see what else can we have. So, like, from the full binary matrix case, we realize that if I have two zeros, if I have two zeros somewhere, like, let me say I have two zeros such that these two zeros and a 1 corresponds to a L-shaped element. Like, let me say that these values are randomly filled: 1 0 1 1 1 1 1 1 0. And let me say that if I have a L-shaped element to start with, such that it contains two zeros and a 1, then in one operation I'll lose out on this one. So in one operation I'll lose out on this one, and this one would change to a 0, and I can further extend this pattern of zeros by one other element, because if I have a surrounding 1 to the, like, if I have a surrounding 1 to any of these cells, so let's say this element is 1, so in the next operation I can always extend these two zeros that I got by this one. So if I have a L-shaped element, like, if I have a L-shaped element to start with that has two zeros and a corresponding 1, then I can always perform x operations, where x is the total number of ones present in the array, because I can always perform one operation such that I'm only losing out only one of the ones that is present in the matrix. And let us see what is the other case. So let me say that there was only 1 0 present in the matrix. So let me try out a simple case. Let me say that there was only a 1 0 present in the matrix. So let's say this element is 0 and rest all of the elements is 1. So no matter how I start with, there is no way in which in the first operation I lose out on less than two ones, because no matter what L-shaped element I can take, there can be at most 1 0 present in the L-shaped element, because I only have one of the zeros that is surrounded by ones. So in this case, suppose I start with this L-shaped element. So in this case, this so what I say is that if I start with this L-shaped element that contains one of the zeros, so in the first step I would lose out on this 0 and I would lose out on this 0. But after that, since now I have two corresponding zeros such that they are surrounded by one of the cell that is containing a 1. So I started with this element as 0 and I made one of its neighbor as 0. So in the next case, what I have is that I have these two cells as 0 and I can extend them in any direction. Like I can extend them in this direction, or I can extend them in this direction. And in one operation, I would lose out on only one of the corresponding ones. So if I select this L-shaped element, the next operation this will become 0. And if I select this L-shaped element, in the next operation this will become 0. Or if I select this L-shaped element, in the next operation this will become 0. So once I have achieved a state where there exists one of the L-shaped element, so like the the loss that you are incurring in changing one of the ones to a 0 is only in the first operation. Like in the first operation itself, like we analyzed the case of a full binary matrix. What happened in that case was, in the first operation you were losing out on 3 ones in just one move, and from the second operation onward, in one operation you can just convert one of the ones to a 0. So you are able to achieve the full 0 matrix in n minus 2 steps, where n is the total number of cells in the matrix. And similarly, we analyze the case of a L-shaped element that has at least one. So the casework is let me say that the number of ones that are present in the matrix is x. So the possible number of ways that I can achieve a matrix of all zeros is by x moves, by x minus 1 moves, or by x minus 2 moves. This x minus 2 moves is the worst case. And how did I find out that this is the worst case? Because I started with a matrix of all ones in this case. If you start with a matrix of all ones, you are able to achieve a matrix of all zeros in the number of moves equal to x minus 2, where x minus 2 is the where x is the total number of ones in the matrix. And this is the worst case because each of the one is already surrounded by a 1. So the worst case that we concluded was x minus 2, and the maximum number of moves that you can achieve is x, because in the one move you are at least losing out on one of the ones. So we have three cases to analyze on. So the three cases are x minus 2 moves, x minus 1 moves, and x moves, where x is the number of ones present in the matrix itself. So let us say that my answer was x minus 2. So in this case, in one of the operation, I have to lose out on two corresponding ones. Like I would have to perform a costlier operation. What I mean by a costlier operation is that there would be an operation such that I select a one, like I select a L-shaped element in which all the elements are 1. So if I am forced to select a L-shaped element in which all the elements are 1, then I would have to perform x minus 2 moves. And let me say that there was at least 1 0 present in the matrix. Let me say that there was at least 1 0 present in the matrix. So in that case, what I can do is that I can let me say no matter how my matrix looks like, and no matter where the 0 is present, let me say the 0 is present over here, so I can select this L-shaped element in the start itself. So if I select this L-shaped element in the start itself, I'm losing out on 2 ones in one operation. And after I perform this operation, I've got two adjacent zeros. And from the further operation onwards, I can always pair these two zeros with any of the remaining ones. So such that I will extend this array of zeros step by step, such that in one operation I'm losing out on at most one of the ones that is present in the array. So if I have at least 1 0 present in the matrix, then my answer would be x minus 1. And if I have if I have a shape, if I already have two consecutive zeros present in the matrix, then I can extend these two consecutive zeros by a 1. There would always be a if there exists a L-shaped initially, let me call this L-shaped that I'm talking about. So if there exists a L-shaped initially, such that the zeros need not be zeros need not be adjacent, because if there exists a L-shaped initially such that two of the elements are 0 and this element is 1. Like, let me talk about this matrix. So in this matrix I have this L-shaped element such that the two of the elements are 0 and this value is 1. So in one operation I can convert all these three to zeros, so I'm losing out on only one, and after performing this operation I'm getting two adjacent zeros, and after I get two adjacent zeros I can always extend this to adjacent zeros by any of the adjacent ones that I have, and at max I would lose out on one of the ones that is present in the matrix in one operation. So these are basically the case work, and how do I implement my solution is that, so uh, my implementation is a bit involved. Like, I think that there can be a way to implement it a bit easier, in a bit easier way. So what I do is, like, I take my input nnm, I take my string, I take my array of a string, the string sn, and I try to count, like, I count the number of ones present in the string itself. So I initialize my answer as 0, I iterate through all of the elements, and if my corresponding element is 1, then I increment my answer by 1. And this is the case work that I'm taking. I'm taking that, is it possible to have L-shaped element that contains at least two zeros? So what I'm saying is that, and this 2 corresponds to, like, this is a flag variable. So if the flag variable is actually initialized to 1 itself, like initially in the start I'm saying that there is no L-shaped element such that two of the elements are 1. So what I mean by that is that I have no L-shaped element in the start such that only one of the element is 1 and the rest of the two are 0. So this can happen in this case, like this is 1 and this is 0. So if I have this case present in the start itself, then my answer would be X. This is the case work that we analyze. If I have a L-shaped element to start with such that only one of the cells is 1, so in that case my answer would be X. And if I have a L-shaped element that contains at least, that contains one of the zeros and the remaining cells as 1, then in that case my answer was X minus 1. So I'm trying out the case work. So this is the flag variable. So flag variable exists. So flag variables is actually initialized to 1 itself, and I iterate through all of the elements present in the matrix, and if the element is 0, then I continue, and if the element is 1, then I try to find the then I try to find all the L-shaped elements that this array element can contain. So let me say that I'm talking about Aij. Well, let me say that I'm talking about this cell. So in this case what I try to do is that for this cell is actually 1 in the initial case. So if this cell is 1, I try to find all the possible L shapes that contain this element. So I try to find this L shaped, and I try to find my this L shape. I try to find a L shape that looks like this, and similarly a L shape that looks like this, and I try all the possible L shapes that contain this element, and I see whether this L shape contains at least two zeros or it contains at least one zero. So if it contains, so do it returns the number of zeros, like the number of zeros present in the, so do it actually contains the number of ones present in the L shape excluding this one. So what I mean by that is that, suppose I am talking about this L shaped. So suppose I'm talking about this L shape. So if these two elements are 0, then my do it would return 0, because excluding this element, because this element is already 1, excluding this element, how many minimal number of ones can I have in a corresponding L-shaped element? So if I can have 0 ones, so if I have a L-shaped element such that only this element is 1, then I initialize my 1 as 0 and 2 as 0. Like I put my these both of these flag variables as 0. So putting 2 as 0 means that I have a L shape to start with, such that I'm losing out only on one of the ones, and 1 as 0 means that I'm losing out two of the ones in one case. So this 1 corresponds to the case of x minus 1 operation, and this 2 corresponds to the case of x minus 2 operation. So initially I was saying that the worst case scenario was x minus 2, but if there exists a L shape such that only one of the element is 1, then I put this flag variable as 0, because 0 indicating that now I need not have x minus 2 moves. I can achieve my answer is in less than x minus 2 moves, possibly in x minus 1 moves. So if I have a L-shaped element such that only that corresponding element is 1 in that L shape, like all the remaining elements are 0, then I initialize 1 equal to 0 and 2 equal to 0. Otherwise, if I have one of the element, if I have a L-shaped element such that two of the entries are 1 and one of the entries is 0, so corresponding to this element I would find that the L shape contains one of the ones. So in that case I initialize my 2 as 0, because I need not have this x minus 2 case, because I can always achieve my answer in less than or equal to x minus 1 operation. So I turned this flag variable off as well. So now I do this for all the elements that are 1 initially, and I check if my 2 variable is on, like this 2 is the flag variable. So if the 2 flag variable is still on, then I need to invest answer minus 2 number of moves. Answer is the number of ones that are present in the matrix itself, and I take this maximum of 0 LL comma answer minus 2, because what if there are no zeros, like what if there are no ones present in the answer itself, then the number of operations is 0 itself. So the maximum, like the minimum the answer can be is 0. So I take, so if my 2 variable is on, then my answer is maximum of 0 operation comma the number of ones minus 2. Otherwise, if my 1 flag variable is on, then in that case my answer would be maximum of 0 comma the number of ones present in the array minus 1. Otherwise, my answer is just answer, where answer is the number of ones present in the array. And how do I achieve this do it? So for do it, I'm trying out on all the possible L-shaped elements that start with this array element. So I check for I plus 1, j plus 1. So this is basically a casework. I try for all the possible L-shaped elements. So this is not, I've not written this code again and again. So I've just copy pasted. I've written it once, I've written the logic once, and I've copy pasted it just 4 times. I just changed it. I just changed this I plus 1 to I plus 1 j minus 1, I minus 1 j plus 1, I minus 1 j minus 1. So that this is not a very hectic code, but my implementation is a bit longer. I think there can be an easy implementation to check if I can achieve this in one possible operation or two possible operation. So the implementation is a bit involved. You can check out other implementations as well, but the logic remains the same. So I'll move on to the fourth question. So the fourth question is an interesting question. So in this case, you are given an array of n integers a0 to an minus 1, and you want to find a subsequence of length m b0 up to bm minus 1, such that this condition holds true for all the values of p from 0 to m minus 1, where m is the length of the sub segments, like n is the length, m is the length of the subsequence that you are selecting. So, and this is the easier version of the problem. So in the easier version of the problem, the AI, the maximum value of AI is up till 200. So let us see what this statement says. So okay, so initially you are given an array of n integers, so a0 up till an, and you have to find, the maximum possible subsequence of length m. So let me say that my subsequence was of length 3. So in that case, b0, b1 and b2. So let me say that my subsequence was of length 3. So in this case, what the statement says is that for all p's ranging from 0 to 2, this condition should hold true. So this condition actually says that like b0 is the corresponding position that you are taking, and it's not the corresponding value. So initially I was confused. So let me say that, let me try out some example. So in this case, let me try this example: 5 4 3 2 1, 5 4 5 2 4 3 1. So in this case my a is given to be 5 2 4 3 1. So let me say that I'm taking this as my subsequence, like this 2, this 4, and this 1. So in this case my array b would look like, this is the first position, 0 1 2 3 4. So in this case my array b would look like 1 3 and 4, because I'm taking the array elements corresponding to the positions 1 3 and 4. So this is what my array b looks like, and this is my initial array a. So what the problem statement says is that you take close up, you take a bp and XOR it with p plus 1, and this should be less than a b plus 1 XOR with bp. So what it says is that for p equal to 0, let's see what this says for p equal to 0. So for p equal to 0, a bp is the value of a corresponding to this position. So abp is the value of a corresponding to position number 1. So the corresponding to position number 1, we have our element 2. So 2 XORed with bp plus 1. So bp plus 1, p, since p I'm taking out p to be 0. So p plus 1 is actually 3. So 2 XOR with 3, and 2 is this value. 2 is this value. 2 XOR 3 should be less than a of bp plus 1. So what is a of bp plus 1 is the value of a corresponding to this position. So corresponding to this position I have a value 3. So this should be less than 3 XORed with bp, and bp is this thing, like, because my p is 0, so bp is 1. So this expression should hold true. So in general, for any b that I'm taking, so let me say that this is my array element a, and this is the subsequence b that I choose. So this is the subsequence b that I choose for. So what the problem statement is saying, if you see what this p corresponds to and what all these terms make up, then you'll realize that what this expression is saying is that you take the corresponding value at, like, you take the corresponding value of a at this position and you XOR it down with this value. So let me say that this is x and this is y. So these are the array indices 0 1 2, and this somewhere over x, and somewhere there is y, and up till n. So let me erase it down. So what the expression xyz, and let me say this is z, and the array b is a subsequent, so it's always increasing. So what the array, like what the problem statement is saying is that you take the value corresponding to this array element x. So you take ax, XOR it with y, and this should be less than ay XORed with x. So this is the XOR operator I'm calling. So you take for all the pairs p and p plus 1, you do this, like you take the array element corresponding to this position, XOR it with the next value, and this should be less than the array element corresponding to the next position and XORed with the current value. So we have to satisfy this constraint. So this, the thing that we can notice is that all the array elements are initially less than equal to 200. So in that case, let's see what can be the maximum difference between two of the values that we can have. So my array is up till a length of 10 to the power 5, like up till 3 into 10 to the power 5. So what it was saying is that x XORed with a of uh, I'm sorry. So this was saying is that ax XORed with y should be less than ay XORed with x. Ay XORed with x. And the maximum possible value that these ax and ay, the maximum possible value that these ax and ay take are actually up till 200 only. So these elements take the value of 200 only, and I can always, like, I can see that the maximum possible difference that XORing this value with 200 can make is by a value of 200. What I mean by that is that suppose I have the binary representation of y as like this, 1 1 0 0 0. So what XORing corresponds to is that, or XORing this, so this is the binary representation of y, and if I XOR it with x, so if this bit is on in x, then my answer would get reduced by 2 to the power of the corresponding position of this bit. So let me say 0 1 2 3 4 and 5. So sorry for that. So let me say that my ax had this fifth bit, like the fifth bit of ax was on and the fifth bit of y was also on. So in that case my answer would, like, the value of my y would get reduced by 5, like 2 to the power 5, because like initial value of y was y, and by XORing it with x I'm losing out on 2 to the power 5 because this bit becomes 0 when I XOR it with ax, and correspondingly for each of the bit, if it was initially on in my y and it became 0, so in that case I would lose out on 2 to the power x, where x is the corresponding position of that bit. So let us see what is the maximum value that we can lose out on. So since my ax is only up to, so since my, just a second, so I say that my ax is only up till 200, and what is the maximum possible bit can this affect in my value of y. So the maximum, like the next maximum power of 2 is corresponding to 256. So the next maximum power of 2 is corresponding to 256. So like 200 can be represented in such a way that this bit is on, and like this bit corresponding to 256 is on, and the rest of the bits are on off. So the maximum bit that can be affected by a number that is less than or equal to 200 is at most this bit, like the bit corresponding to array element of 256. So the maximum bit that this can affect is only up till, like, the maximum that my ax can influence my value of by my y is by only a value of 256. So initially if I start with my array, if my initially if I start with my value of y as 10 to the power 5, then after taking a XOR of y with ax, then after taking a XOR of y with ax, the maximum that it can be reduced by is by 256. So the minimum value of this expression would be 10 to the power 5 minus 256. That's it. My y, the value of my y cannot go lesser than this expression, 10 to the power 5 minus 256, because I say that the maximum bit that this a to the power x can affect in my value of my y is the bit corresponding to the value 256. So at maximum it can turn down this bit, like it can turn off this bit. So if my bit was initially on in this yth and my yth element. So, and this bit also is also on in my AX element. So this bit would actually turn out would actually get turned off if I XOR my AX with Y. So the maximum the AX can affect my Y is by a value of 256, because that is the maximum bit that it can affect. So what I need to find is that a corresponding X for each of the value of Y. So let me say that AX XORed with Y, AX XORed with Y is less than AY XORed with X. So what I'm saying is that since the value of my Y can at most be reduced by 256, so I need to find a corresponding X such that this value lies somewhere in the range of X has to be greater than or equal to Y minus 256, because these array elements cannot change my. So let us say if the question was only Y less than equal to X, so in that case I would take all the pairs such that Y is less than equal to X. But my question is AX XORed with Y should be less than AY XORed with X. So the maximum this AX and can affect my value of my Y is only by a factor of 256, and similarly the maximum this AY can affect my X is by also by a value of 256. And combining all of these two combining all of these two the maximum difference that I can have between my Y and my X is only by 256, because this AX can turn off certain number of bits in my the value of Y, and this AY can turn off certain number of bits in my this corresponding value of X. So at max the difference of X and Y can at most be 256. So what I do is that I run a brute force solution, that is I try to take all the possible subsequences such that the maximum possible difference among the array elements, like the maximum possible difference between B0 and B1 and B1 and B2, and similarly BM minus 1 and BM minus 1 and BM minus 2 is at max 256. Because if we see this expression, then we have noticed that the maximum possible difference that I can achieve by XORing this BP plus 1 with ABP and my BP with ABP plus 1 is at most 256. So my value of BP and BP plus 1 cannot exceed the difference in values of my BP and BP plus 1 cannot exceed 256. So this is what I'm saying, and I will run a brute force solution and see if this condition gets satisfied for each of the solution. So I'll show you my implementation, how I implement this, and this will be a bit clear after this. So I implement it as a dynamic programming solution. So initially what I do is that I take my input array and I create a TP vector and I initialize with 1, because you can always take the last element, because for the last element you need not pair it with anything. So the minimum length of any subsequence, so let me clear this up. So 0 1 2 3 4, so you can choose any subsequence of length 1. So that would also always be a beautiful array, because you need not pair it with you need not pair it up with anything else. You can always choose a subsequence of length 1. So I initialize my DP array with length of 1 and I start iterating from the last element itself. So for the last element I iterate through all the corresponding elements starting from I plus 1, and I iterate up till a maximum of I plus 257. So for that case I check whether this condition is satisfied or not. So the condition is the value of so I explained it over here. So I explained it over here that what I want is that this value AX XORed with Y should actually be less than AY XORed with X. So this is what I'm implementing over here. So I say my AI XORed with Z, like AI is the value corresponding to the position I, and since my J is the array element that I'm taking, like since I have to consider only an increasing subsequence, so I take this I as my last subsequence that I'm considering right now, and I try to extend this subsequence by another element. So I take a dynamic programming solution. So right now I'm working with array element Y, and I try to see if I can extend this subsequence by any other subsequence or not. So I try out all the possible values of I plus 1 up till I plus 257, the minimum of n comma I plus 257, and I check whether my condition is satisfied still or not. So I check whether AI XORed with J is less than AJ XORed with I. So in that case, I extend my DP solution with dp of I is equal to max of dp of I comma 1 plus dp of j. dp of j corresponds to the maximum possible subsequence ending at like starting at this array element j, and I increment it by 1 because I'm also considering my array element I in this case. So what I mean is that, let me see. So what I mean to say is that I start iterating from back. So initially all my dp values are assigned to 1. So the maximum possible subsequence starting at this array element and considering only the suffix is of length 1. So I check for this element. Can I extend this element by any other element that exists to its rightmost half, and that exists in it right half? So if I say this element is Z, so I check whether X, right? I check whether a X XORed with Y is less than a Y XORed with X. So in that case, I can extend this value, like I can extend this subsequence by the subsequence is starting at this position. So in that case, my dp of I would become maximum of dp of I, like the maximum, since I have to check for all the possible j's lying in the range from I plus 1 to I plus 257. So I check whether I can extend this solution or not, and if I can extend this solution, I try to extend it in such a way that the value of my dp of I is maximum. So in all the cases, I take my dp of I equal to maximum of dp of I comma 1 plus dp of j. dp of j corresponds to the length of the subsequence starting from array element j, and I extend it by the ith element. So this becomes 1 plus dp of I, and then I output the maximum element present in my dp array itself, because I can start at any of the subsequence that I want, and I take the subsequence of the maximum length. So the answer would be the maximum array, the maximum value contained in my dp vector. So that's the solution for problem D. If you have any doubts, you can ask me in the comment section itself. So thank you.